I'm Dr. Kushmita Kundu. I'm an assistant professor of chemistry in SBIST. Okay. So in the last class we have covered the topics of UV spectroscopy. In today's class we will be covering rotational and vibrational spectroscopy. Okay. So spectroscopy is basically the study of the interaction of a matter, the incident light. Whenever an incident light falls upon a matter, what is the reaction or what is the interaction that are being, that is the study of that interaction is known as the spectroscopy. Okay. So if there is a matter and some light falls upon it, so some amount of energy, light in the form of energy, so some amount of energy will be absorbed by that matter and the rest amount of will be transmitted. Right? Now after absorption, what happens? After absorption, those molecules which are at ground state, they will be excited and they will be promoted to the excited state, right? They will absorb energy and they will be promoted to excited state. Now during this excitation, there will be some physical changes in the molecules. Either the molecule can rotate through their own axis or they can vibrate, right? Now if the molecules are rotating on their own axis, then that study will be known as rotational spectroscopy. And if it vibrates, then that study will be known as vibrational spectroscopy. Okay, from rotation, it is known as rotational spectroscopy. Rotational spectroscopy. And for vibration, we get vibrational spectroscopy. We will get vibrational spectroscopy. Okay, if it rotates, then rotational. If it vibrates, it is vibrational. So, in case of rotational spectroscopy, the molecule will follow two different models. First one will be rigid rotator models. Okay. First one will be rigid rotator model, and second one will be non-rigid rotator. Rigid rotator means when the bond length for a diatomic molecule is fixed. That is known as rigid rotator model. And non-rigid rotator means when the bond length is not fixed, bond length is variable, then that model is known as non-rigid rotator model. Okay. So in case of rigid rotator model, the energy expression E rotational would be Bj into J plus 1. Bj into J plus 1, where B is rotational constant. B is rotational constant and J is rotational quantum number. Rotational quantum number. P is rotational constant and J is rotational quantum number. Okay. And value of B is h square divided by 8 pi square I, where h is Planck constant, and I is the moment of inertia. I is the moment of inertia. The value of I is mu r square. Okay. Where mu is the reduced mass. Mu is the reduced mass. Mu is reduced mass, and mu equals to m1 dot m2 divided by m1 plus m2. For a diatomic molecule having the mass of m1 and m2, the mu reduced mass would be m1 dot m2 divided by m1 plus m2. Okay, and r is the distance between the two molecules. Now, from the energy expression, E equals to Bj into J plus 1. Now, when the value of J equals to 0, then the value of E would be 0. And when the value of J equals to 1, E would be 2p. J equals to 2, E will come as 6p. Okay. So that's how the energy levels, rotational energy levels will come. And these all are in the form of centimeter inverse frequency, in terms of frequency. Okay, so these will be the rotational energy levels. Now, if we think that a molecule makes a transition from J equals to 0 to J equals to, makes a transition from J to, let's say J to J plus 1. It will make a transition from J to J plus 1. So what will happen? Energy of Aj would be Bj into J plus 1, right? And for J plus 1, it would be Bj plus 1 into J plus 1 plus 1, right? So, Bj plus 1 into J plus 2, that would be the value of Ej plus 1. Now, if we find out the energy requirement for this transition J to J plus 1, what will it come? So, del E would be Ej plus 1. Del E would be E final minus E initial. So, Ej plus 1 minus Eg, right? Ej plus 1 is Bj plus 1 into J plus 2 minus Bj into J plus 1. If we solve this, it will come as 2B into J plus 1. Okay. So, this is the energy requirement for the transition which is happening between J to J plus 1. Okay. Now, if we put the value of J equals to 0, J equals to 0 means del E J equals to 0 to 1, the transition is happening between 0 to 1. So, del E would be 2B, right? If the transition is happening between J equals to 1 to 2, then the value of J would be 1 and the energy will come as 4B, right? 2B, 4B, and when the value of J equals to 3, the del E will be 2 to 3 and it will come as 6B, right? So that's how we will calculate the energy requirement, and this all will be in the form of centimeter inverse. Okay, so that's how we will calculate the energy requirement for each transition, J0 to 1, J1 to 2, J2 to 3. That's how we will calculate the energy transitions. Okay. Now, if we now discuss about the vibrational spectroscopy. Vibrational spectroscopy also follows two models. One is harmonic model. And another one is anharmonic model. And the energy requirement for vibrational energy levels, energy is V plus half of h nu, where V is vibrational quantum number. V is vibrational quantum number. Like J was rotational quantum number. Okay. And h is Planck constant and nu is the oscillation frequency. Okay. Nu is the oscillation frequency. Now, the energy expression is E vibrational equals to nu plus half of h. Now, when the value of V equals to 0, then the energy would be half of h. Now, the interesting part is when the value of J equals to 0, in case of rotational energy levels, the energy was 0. But in case of vibrational, the energy is half of h. That means in vibrational spectroscopy, the energy is never 0. That means the molecule is never at completely rest in case of vibrational spectroscopy. Okay. And for enharmonic, E vibration is V half h nu minus v plus half square xc and h nu. Now this xc is known as anharmonicity constant. Xc is known as anharmonicity constant. So all this energy expression that I have written here is derived from the Schrodinger wave equation. Okay. So this was all about rotational and vibrational spectroscopy. In the next class we will be covering a new topic. Thank you so much.